hello everyone. In this session what we are gonna do is we are gonna talk about another new data structure, and the name of the data structure is heaps. So in real life we have seen heaps many a times. Like when you see a mountain, you can see that the mountain is basically in a triangular form, and that shape we call that form as a heap. And similarly you can see that in the example I have taken here, the fries forms a triangular, like this kind of conical shape, right? This conical shape we call them as a heap. So in this whole session we are going to talk about what is heap, how to perform operations in a heap, and how to build heap. We will talk about all about these things in the further part of the session. But to understand heaps, to understand the data structure of heaps, we need to understand the concepts of priority queues. We have studied queues in our previous sessions. We have studied stack, we have studied queue, and in that session, in the queue session, I have said you that we will study enhanced version of queue, and that version is priority queue. So I said in that session I said that we will study about it. Now to understand the overall concept, the overall working of heap, we need to understand the concept of priority queue. So priority queue is nothing but the word priority queue is made up of two things, priority and queue. So priority is nothing but, let's say that you have a set of things, you have n number of students, you have 10 students. Now you wanna pick the best out of him. So this creating this sort of condition, picking best or picking the worst, or picking a student who has the most weight or height. So making some parameters, making some conditions which makes student to align in a ascending or descending order, or in a fashion where we can pick easily that particular thing is known as priority. And queues, we have already studied queues. Queues is a FIFO data structure, and the first element which comes in will go out. But the concept of priority queue and how a general queue is different from priority queue is that in priority queue we will create some conditions, and based on that conditions we will pick the element which suits our conditions first. After that we will pick the second element which suits the element the second most, right? So we will pick the first element which suits our condition, whatever the conditions we are creating. If it is satisfying this particular condition, then we will choose that first. After it we will think of other elements. Whereas in general queue, in normal queue, what we used to do, we will take whatever the elements irrespective of the priority or whatever it might be. If the element is coming first, we will choose that element first. So this is the basic difference between general queue and priority queue. In priority queue, what we will do is that we will create some priority, and based on this priority we will take elements. This is a basic understanding of a priority queue. And if you want a real life example, let's say that there is a college, and in college we are having only two seats. So in college we are having two seats. Let's say that this is seat 1 and seat 1 and seat 2. So these are the two seats. Now for these two seats, the total number of applied applications are, let's say that 4 students have applied for these seats, and the student 1 rank is, let's say, 10,000, student 2 rank is 500, and student 3 rank is 100, and student 4 rank is, let's say, 50,000. So here we need the total number of applicants are 4 and the available seats are 2. Now we need to take those elements which has the least rank. It means that their score is high. The person who is having the least rank has scored the most, right? So we need to bring the most talent out of it. We need to take the only talented person in our, we want to take only talented person in our institution. So what we will do is that we will sort this element. Generally what we will do, we will sort, and after sorting we will take the rank, we will take the student who has the least rank. So in this, first of all we will take S3, we will assign S3. For seat 1 we will assign the S3 student first, because he has the least rank. After that we will check among these 3 students who has the least rank. S2 student has the least rank, so S2 will get assigned for second seat. So this is how assignment will work. So in this basic example, what I have created is, I have created a priority, and the priority says that the person who has the least rank will go in first, will take the seat first. This is the basic concept, this is the basic understanding of a priority queue. So priority queue, generally what we do, we will sort elements. So instead of performing sorting operation, what you can do is you can directly create a priority queue, and priority queue will take care of everything. You don't need to perform sorting operation, create sorting algorithms. You don't need to do that. We don't need to do sorting, but priority queue will take care of everything, because we have created this concept of priority queue, and this will take the elements which has the least value, right? And the second best example I can think of is that, let's say that in a hospital we have a bed, and there are 3 patients. Let's say that the patient 1 has came up for only checkup. He want to do a general checkup, so he first came. After the second patient came, and he has some fever you can say, or he has cold. And the third patient came, and he has some severe injuries. He got into some accident. So in this, the first came patient is for checkup, and the second patient is for he has some cold or fever, and the third patient has some serious injuries. Now the question is, which patient you should take first, irrespective of who's come first or who's come at last. Irrespective of that, who will you take first? You will take the patient as the first patient based on their emergency. If the patient is in an emergency condition, then you will take him first. So I will take the third patient first, after the second patient, after the first patient. So this is the priority order, and priority can be anything. Here I have taken the priority in terms of emergency. In the first example, I have taken the priority in terms of rank. So this priority can be anything. And you have to define the priority in whenever you are creating your priority queue. You need to give and define your priority. And when you are creating a primitive data type, I will talk about how we can create priority queue. And when you create a priority queue for primitive data type, what are primitive data types? Integer, float, double, character. This data types, if you want to create a primitive data type priority queue, then what will happen is that it will take the least value first. Java innately takes the least value first. After it will take the next greater values. So here, before going to the operations, let me clear the screen here. So how we can create priority queue in our Java collection using our Java collection framework. So what we will do is that, if you remember, we used to create stack by just writing stack after angular brackets. In the angular brackets, we used to do data type. Similarly, to create priority queue, what I will write is that, first of all, I will import the package. I will import java.util.star. After importing, what I will do is that I will create my priority queue in the program. So I will create priority queue, and I will write the data type. Whatever the data type I am using, I will write the data type. After that, I will write my name. Let's say that my name is pq is equals to new priority queue, and angular brackets after parenthesis. So this is how I will create my priority queue in my Java program. Now let's say that the data type is of integer type. So if I create an integer type and I am adding, let's say I'm adding pq.add, and here the operations is as same as q. In q we had operations like add, we have operations like q, we have operations like remove, like peek, all those kind of operations we had, right? Similarly, in priority queue we have those same operations, but the only difference is the time complexity will change quite a bit. We will talk about it, but here let's say I'm adding element 10, I'm adding element pq.add 100, after I'm adding let's say 0. Now if I want to print element, you can see that the output will be 0, 10, 100. I will get the elements in my ascending order, because internally what Java will do is that it will take the elements which has the least value first. This is what my Java will do internally. So the element which has the least value will go into my priority queue first. After the next element will come in, after the next greater element. Like this, my element will get added into my priority queue. And if you want to visualize priority queue, a priority queue will look same as a queue. in queue we had like a front and rear value, right? This is my front and this is my rear. So similarly we have the same thing, and if I want to peek, if I want to perform operations, then the first element is front element, right? So if I perform peek operation, then 1 will get printed here, but the only difference is that priority. Okay, in queue we don't have any priority. In priority queue we create some conditions, and based on that criteria we will add elements. So this is the basic difference, and overall the working is overall the same. Now let us talk about the operations. Operations, how we like perform operations. So let's say I have created priority queue PQ, right? So what I will do is that I will write PQ dot add, and I will insert element. I will insert elements here, and as I add elements, let's say I'm adding element 1, 2, 3. So based on the priority, the element will get added, and if I want to perform peek operation, PQ dot peek, then my element will be 1. Whatever the element present on my front element, though that element will get printed. Now if I want to remove element, then the element which get inserted first will come out. Okay, this is the basic. And the time complexity, if you observe that we got constant time in queue, but in priority queue the time complexity will become big of log n. You need to remember this. For add and remove, the time complexity is big of log n, and for peek the time complexity is big of 1. So this is about priority queue. Now let us see how we can write or code priority queue in our program. So in this, first of all I will import java.util.star. After it I will write my class, overall my class, public class Java programming. In this I will write public static void, my main function, public static void main string args. Now in the main function what I will do is that I will create my priority queue first. So the first step is create priority queue, create my priority queue. So I will write capital P priority queue, and I am creating, let's say I am creating integer type. So I will write integer and the name of priority queue, PQ is equals to new priority queue. So by just writing this line, my JCF, my Java collection framework, will create a priority queue in my program. Now let's say I am adding elements. I am adding elements randomly, pq.add and 10. After that pq.add, let's say I am adding 0. After that pq.add 2. I am adding randomly. So after adding my elements into my priority queue, what I am gonna do is I will print those elements. So to print elements in my priority queue, I will run a while loop while my PQ is not empty. PQ is not empty. What I will do is that in the while loop I will print system.out.print. Here let me remove ln, and here I will peek each and every element. So peek and give a space here. After that what I will do is that I will remove the front element. I will remove the front element from my priority queue. Now here let's say I am having 1, 2, 3. So in this queue what I will do, what I am doing is, whatever the element present in my front element, I am printing that element. After that I am removing it. Now my front element will become my second. So this second element will come at first position, and after that I am peeking, and after that I am removing. Like this I am running my loop, and this loop will continue until I hit my base case or my condition become false, and that condition is my priority queue should become empty. If it is empty, then I will stop my loop. So this is what I am doing. Now if I run this code, here you can see that I am adding randomly. I am adding randomly here 10, 0, 2. Now what my priority queue will do is that it will take 0 first, after it will take 2, after it will take 10. So this is what internally my priority queue will do. Now if I run this output, then my output should give me 0 first, after that second, after that 10. Now let me save. Here it is showing some kind of error. Why it is showing error? Syntax error. Why it is showing syntax error? pq.remove. Let me save and run. Yeah, you can see that I got the output. I think that's a glitch, but yeah, you can see that you can see the output as 0 to 10. So this is how I will print my element and add elements into my priority queue. Here you can see that I have performed the 3 operations. I have performed add operation, I have performed peek operation, after that I have performed remove operation. Okay, now let us talk about another concept, which is, in primitive, for primitive data types, I have created integer data type priority. I can create integer priority queue, float priority queue, boolean. I can create like this. For primitive data type, I can create priority queue, and after creating priority queue, it will take the least element, because my computer will understand the overall working of a integer. It will understand which integer is smaller, which integer is greater. Now my question is, if you see the previous lectures, I have passed in the place of, whenever I am creating queue or another data structure, I am not passing, in some cases I am not passing a primitive data type, I am passing an object. I am creating a class and I am creating the object of that class in my main program, and in the place of primitive data type, in the place of integer, I am passing a object. Then what will happen? How my priority queue will understand that this element should go first because it is smaller, and how this element will go second because it is greater than the first element. How it can understand? So let's say, for example, to make it, I don't want to make it confusing to you guys. So for example, let's say that I am creating a class, static class student. So here I am creating a class, and each student will have name, string name, after that string name, after it, let's say int rank. Now I can create a constructor here, student, public student. In this I will pass my initialized function. Let's say that string name, after it int rank. Now after it, what I will do is that I will give this dot name is equals to name. After that, I am initializing the values. Whatever the object is created, I am initializing its values. So this dot rank is equals to rank. Now after it, now here let's say that in the place of integer, I am passing student object. Let's say that I am creating student. Here I am creating student. Here I need to give student. Yes is equals to new student, right? And here let me give the name as some Jabir. Let me give the name Jabir. After rank is, let's say at 100. Rank is 100. Now here I need to pass a object. So here you can see that I have passed integer class. Now I want to create a priority queue of student. So here I am writing student. Now the question is, how my priority queue will understand which student it should take first? Because for integers, my computer can understand that this number is smaller, this number is larger, it can understand. But here you can see that I am having a class, and how my priority queue can understand that this student is having less rank, this student is having some greater rank. So I will take the student which who has the less rank. How it can understand? So to make a class comparable, to pass objects, what we will do is that we will create a comparable class. We will inherit the properties of comparable. In Java, there is a interface called as comparable, and this comparator interface is used to compare objects. So by inheriting the properties of interface called as comparator, we can compare objects. So how we can compare? Let's say that here I will write implements. After writing implement, I will write comparator. Here I will write comparable. Comparable is an interface. In this I will pass my student class, student, and after it, in the program, what I will do is that I will, let's say I want to compare based on rank. So what I will do is that I will perform function overriding. So I will write capital overriding. Now after it, here I will write a function public int compare to in this I will pass a let's say I am passing student rank, int rank. So here what I will do is that I will return this dot rank minus this s2. Here I am passing, let's say I am passing student in the function. I am passing student, right? So student s2. So here what I will do is that s2 dot rank. So this function, this whole function will compare my whole student object based on his rank, right? After what I will do is that here I have created my priority queue. Now my priority queue can compare because I have inherited the properties of comparable interface. Now what I will do is that I will add pq.add student, and here I will pass a new student, here new student, and I will pass my function parameters Jabir. After it, let's say his rank is 100. After it, I will add a new object pq.add, and here new student I am creating in the pq.add. Here I am creating new students as my object, and this new objects will get stored in my priority queue. And how it can store, how in what fashion it will get stored based on rank. Now if I want to store based on the name, the string name, then here I will pass this dot string name after s2 dot name. So this, instead of writing rank, I will just write name, and this will sort, this will compare based on name. If I want to compare with respect to rank, then I will write rank. Okay, so here I will pass, let's say that I am passing name as Moin, and here I will pass rank as 90. After that I will again pass pq.add new student, and I am giving name as Rizwan, and here I will give rank as 80. Now I want to print this element. So how I can print? I will write while my pq is not empty. In this, what I will do is that I will peek the element, and here I can't directly write pq dot peek. Here I can't. If I write this, then you can understand that here I am storing objects. So if I print just write, if I write pq dot peek, then it will return an object. It will return the address of the object. So here what I have to do is that I will write rank. Now if I want to print name, then what I will do is that I will write along with rank, let us give name. So pq dot peek and dot name, and give a space like this. Yep. So here along with name I am printing their rank. After it, I am removing pq dot remove the top element, whatever the top element I am having. Now if I run this program, then my output should be, first of all I will get rank 80, after rank 90, after rank 100, because the element which has the least value should come in first. So let me save and run. Okay, after printing each and every element, let me give the next line also. So let me save and run. So you can see here, let me also give a space here, space, after it again. Okay, now if I run this, then you can see that my output will be, first of all I got Rizwan because he has the least rank, after it Moin, after it Jabir. So based on rank I am adding elements. Now if I want to add elements based on name, then in the place of rank I will write name. By just writing the name, my element will get sorted based on name. So this is how we will compare objects, right? So this is the whole working of comparable interface. Comparable interface is used to compare objects in my priority queue. Whenever I am passing my elements, if I want to compare objects, then you have to keep this in your mind that I am gonna use our interface, and the name of that interface is comparable. After it, in the class, whatever the class I am creating, which is to be compiled, whenever I create objects of that class, those objects will get compiled. So if those objects are getting compiled, then in that class program, what I have to do is I have to write this line. This line is must, this function is must, and based on this function my objects will get compiled. I hope you have understood how we compare objects in Java collection framework. Now up to now we have studied what is priority queue, how we generally perform operations in priority queue. Now we have completed the overall working and the understanding of priority queue. Now let us talk about heaps. So I have said you that whenever we see this types of data structure, this kind of data structure, a mountain or conical or triangular data structure, this form, we call this form as a heap. And you can see that heap, these two diagrams, this diagram 1 and diagram 2 are the example of two different types of heaps. Now if you observe these two things, you can ask, oh Jabir, this is very similar to binary trees. So what is the difference between a heap and a binary tree? Yeah, a heap is a, you can say we visualize heap using binary trees, and we implement heaps using array list, and the working of a heap is very similar to priority queue. This three sentences sound very complex, right? So here we are gonna use the concept of three different data structure. One is we are gonna use the concept of binary trees. Second is we are going to implement a heap using array list. This is my second data structure, and the working of my heap is very similar to the working of priority queue, right? I hope you have understood. So this, you can see, you can understand that heap is a sort of combination of these three data structure: binary trees, array list, and priority queue. Now this might sound complex to you guys, but believe me when I say that a heap is very easy data structure when compared to the data structures up to now we have studied. Like we have studied hierarchical data structure, BST, AVL trees. When compared to those, a heap is a very easy to understand data structure because it has some fixed rules. The logic is fixed, that is why it is very easy to understand. Okay, now we have two different types of heaps, max heap and min heap. So in max heap, the root element will have the highest value, and whatever the elements coming in underneath of my binary tree, those values should be less than my root node. And if I say in other terms, the parent value should be greater than child value. If this is the condition, if this condition is satisfying for my whole tree, then that is a max heap. In min heap, what will happen is that my parent value should be less than my child value. If this condition is satisfying for my whole binary tree, for my whole given structure, then it is a min heap. Now let us understand what is the actual definition of heap. I have shown you that if I am seeing this structure, this conical or triangular structure, if this structure is forming, then it is a heap. Okay, now let us understand what is the formal definition of heap. So a heap, first of all, has three properties. Whatever the structure you are having, if that particular structure is following these three properties, then that structure is said to be a heap. Okay, and what are these three properties? The three properties are, the first property is it should be a binary tree. It should be a binary tree. It means that for a given structure, it should not have more than two roots. If it is having more than two branches, then it is a tree, but it is not a heap. Right? So the first condition is it is a binary tree. It means that at max it can have two children. Okay, and the second property is it should be a complete binary tree. And I think this is the first time you are like listening the word complete binary, this term complete binary tree, and I think you haven't heard it. This is the first time we are hearing it, right? So a complete binary tree is a binary tree in which all levels are completely filled except the last one. The last one don't have to be necessarily completely filled. It can be filled or it doesn't have to be filled, but the filling process should, for the last node, it should go from left to right. If this condition is satisfying, then it is said to be a complete binary tree. I hope you have understood the definition. It means that let's say that you are having a tree. You are having a tree and let's say this is the tree I'm having. Now you can see that in tree we have different segments, we have different level. So for each and every level, that tree should be filled. What I mean by filled is that, let's say that this is a parent and it should have two children. If it is not the last level, then it should have two children. If it is not having the two children, and if it is not at the same time not the last level, then it is not said to be a complete binary tree. And similarly, for the last level, this is the last level, right? In the last level, it doesn't have to be necessarily completely filled, but it should get filled from left to right. So this structure is said to be a complete binary tree. Now let us take examples. So I have told you that for each and every level, the tree should be filled, and if we got the last level should get filled from left to right, and it doesn't have to be completely filled. Last level doesn't have to be completely filled. Now let us see that I have taken different structures, and by you can see checking whether the given structure is CBT or not, we will understand what is a CBT better. So if you observe the first structure, in the first structure the level 1 is completely filled. In the level 1 I am having one parent node, okay, and in the second level the parent node is having two children, okay, it is filled. Now last level, you can see, if you observe last level, this particular node is not having children, okay, but what does the rule says? The rule says that the last one which is filled from left to right. It means that last level doesn't have to be completely filled. It can be half filled or not filled at all, but the filling process should happen from left to right. So you can say that first of all I have filled this left node, after its right node, okay. So level 1 is filled, level 2 is filled, and in level 3 the filling is happening from left to right. From left to right, the process is happening in a structured sequence manner. So this structure is a CBT. Now if you observe the second structure, my level 1 is filled, level 2 is also filled. Now if you observe the level 3, in level 3 first of all the left side is filled, after its immediate next node is not filled. I have come directly on the extreme right. I have come on the extremely right side, and because of you can see that it is not going in a structured format, not in a sequential format. Because of this is not a complete binary tree. I hope you have understood. Now in the third diagram, if you observe, the level 1 is filled, okay, the level 2 is also filled. Now in the last level, you can see that first of all I have filled the left element, after the second left element, after the third element. So I am going sequentially, step by step, from my left side to my right side. My filling is happening from the left side to the right side. So this level 3 is also satisfying the property of a CBT. So if all the levels are satisfying, then it is considered to be a CBT. Okay, third diagram is CBT. Now let us talk about the fourth diagram. So level 1 is satisfied, okay, level 1 is satisfied. Level 2 is also satisfied, okay, level 2 is also satisfied. Now if you observe level 3, I have filled the left element, after the next element. After the next element should come here, but instead of filling here, what I did is that I haven't filled here and I gone to extremely right side. Because of this disorder, my third level is not following the property of CBT, and because of this is not a CBT. Now let us see the fifth diagram. If you see the fifth diagram, level 1 is satisfying, level 2 is also satisfying, and in the level 3 I am filling my element from left to right in a sequential, in a step by step format. So level 3 is also satisfying. So this is a CBT. Okay. Now if you see the sixth diagram, level 1 is satisfied. Now level 2 should have two children, but this child is missing. So if this child is not missing, I don't need to check any more further. This is not a CBT. So this is the concept of CBT. I hope you have understood what is CBT. Now this is the second property. The tree, whatever the tree I am having, that tree should be a complete binary tree. I hope you have understood the definition and overall the understanding of a CBT. Now it should also follow the third property. I have said you that we have two types of heaps, min heap and max heap. Here I need to write min heap, not max. So in min heap, if the child is having value greater, each child is having greater value than its parent node, then it is said to be a min heap. If you observe this diagram, you can see that this is my parent value, right, and it is having two children, children 1, children 2. So this children is having, you can see that children 1 value is greater than parent node, and children 2 is also having parent node. And if you observe this as a parent, as an individual parent, its children is having the values greater than its parent value. So this whole tree is a binary tree, is a complete binary tree. You can see that the filling is happening level order, level wise. So the first property is satisfied, second property is satisfied, and the third property says that it should follow either these two rules. So it is following the property of min heap. So this whole structure is considered to be a min heap. I hope you have understood. Now if I got a condition where my parent value is great for each and every node, the parent value is greater than the children's node, then it is a condition of max heap. So this is a formal definition, this is a perfect understanding of what is a heap. Now let us see that in these two structures which one is heap or not, and by doing that our understanding of heap will get even more better. So if you observe the first diagram, the two given 1 and 2 diagrams is binary tree, and 1 and 2 diagrams are also complete binary trees. Okay, these two properties are satisfied. Now I need to check my third property. The third property says that either it can be a min heap or a max heap. If it is not following the properties of both either min heap or max heap, then it is not a heap. Okay, so let us see the first structure. You can see that this is my parent node and its child value are less. And similarly, if you see this as an individual parent, his child, this node's child is also having less values. So this is a heap, because the parent value is greater than or equals to my child value. So this is a max heap. This is a condition of max heap. Okay, so it is a max heap. Third condition is also satisfied. If these three conditions are satisfied, then the given structure is a heap. Okay, now if you observe the second diagram, you know, it is also a binary tree, it is also a complete binary tree. But if you observe this, for this parent, the two child's values are less. Okay, so for this given segment, the condition is satisfied. Now let us see this segment. So for this segment, let's say this is my parent and this is my child 1 and child 2. Okay, child 2. Now for max heap, if this is a max heap, then my child value should be less than or equals to parent. So 4 is less than or equals to 5. Okay, condition is satisfied. Similarly, the second child C2 should be less than or equals to parent. You can see that 6 is not less than or equals to 5. Because this condition is not satisfying, this is not a heap. This is not a heap. I hope you have understood how we can check whether the given structure is a heap or not. Now, one more thing is that, let me go to the structure, let me go to the heap structure. You need to remember these lines. We visualize a heap in the form of a binary tree, and we implement a heap using arrays or array list. This is the thing you need to remember. Whenever we are imagining a heap in our head, we think of it as a binary tree, and whenever we are implementing a heap in our code, we will use array list. Now you might ask why we can't, like, we implemented binary trees, we implemented binary search trees by creating a node class, and after that we have implemented using the general method. But why can't we do the same thing for heaps? The question is why? Because, let us talk about here, because why we are not going to use the same methodology that we followed in binary trees, binary search trees, is that, let's say that this is a heap. You can see that this is my heap structure. Now if you observe that this is a min heap, and the definition of min heap is that it should be a binary tree, CBT, and the third condition is that parent value should be less than or equals to my child value. If these three conditions are satisfying, then it is a min heap. Okay, now I want to insert one node here. So the insert, what I will do is that if I am going with the generally class node method, if I am creating a node and after that I am inserting, if you observe the insert methodology, what I used to do in binary trees, binary search trees, what I used to do is that I will go level wise and I will check. And one more thing is that I should satisfy the properties of CBT. If it is not following the property of CBT, then it is not a heap. So I will check from left to right. I need to add elements. So I should add this one node in the last left value. I should add here in this position. I should add. I can't add in this position, because if I add here, it shouldn't follow the property of CBT, right? So I should add in this direction. So what I will do is that I will add 2, 3, 4, 5, 10, and I will add 1. So to add this on the last element left side in a sequential manner, to add this in a sequential manner, I need to iterate each and every node. So this iteration, this iterative or recursive, whatever the function I am creating, this thing is fixed. I need to iterate at each and every node. This iteration, this iterative process will take, let's say I am having n nodes, then this only iteration process will take big of n time, right? This will take big of n time. Now after that, one more thing is that if you observe this structure very clearly, my heap condition is not satisfying here. So after adding, I need to fix my heap, and to fix a heap again, I need to perform operations. I need to take this node on the top side, because 1 is the least element. If it is a least element, then it should become my root node. Again, I need to swap elements, do some operations, blah blah blah. So to fix element, again it will take some extra time. This is why we don't use a general approach with general node. By creating this thing, we don't follow this, because I need to iterate through each and every element. After iterating, I need to again perform some extra operations, and that extra operation will take extra time, and overall I won't get a efficient time complexity. Because of this, I don't use a general class approach. I will use array list or arrays. So in array list or arrays, how we visualize is that, how we represent a particular given heap in an array list is that we will create a array or array list, whatever you want, and I will add elements in this order. First of all, 2 will go in after 3, after 4, after 5, after 10. So this is how I will visualize elements in my array list. And one more thing is that you need to keep this in your head. This is the property. This property is very important property, and the property says that if for a particular node, if it has an index, let's say its index is I, then its left child index will become 2i plus 1, and right child index will become 2i plus 2. It means that, let's say that here in this the indexes are 0, 1, 2, 3, 4, right? So for this particular node, if this is a node, then its right children will be 2 into 0 plus 1. It means that I will get my right children here, after left children here, after right children here. So here you can see that 0, 1, 2, 3, 4, and by this property I will perform many operations, and if the index is I, then the left child index will become 2i plus 1, and right child index will become 2i plus 2. Okay, so this is how I will visualize a particular heap in my array list, and this is how I will iterate using this indexing property. I will iterate through my overall heap. Now let us talk about how we can add elements in my heap. Now let us see how we can insert a particular element in a heap. So this is a heap, right? And if you observe this is a min heap, and in min heap the condition is that parent value should be less than or equals to child value. This is the condition. Now what I told you that we visualize a given heap in the we visualize it in the form of binary tree, but we implement it using array. So what I will do is that I will this is the given array, right? So I will add elements. This is the visual implementation. This is the array will look like 2 3 4 5 10. I will iterate through each and every element, and if you see this is the representation in terms of array. This is the representation in terms of array of my heap. Now let's say that I wanna add 1. So adding element in my heap is a two-step process. The first step is add at last. Whatever the elements you are gonna add it at last, and after that the second step is fix heap. So what is the meaning of fix heap? Let's say that here how many indexes I am having, 0 1 2 3 4, and I want to add 1. So I will add 1 at the 5th index. So I will create a new index. After that I will add 1 here. After that, this is my 5th index. Now let us observe the heap. So I have added my heap in the 5th index, 0 1 2 3 4. On the 5th index I have added 1. Okay, now let us observe this heap. So if you observe this heap, is it following the properties of min heap? The answer is no. The heap is not following the conditions of, you can say, it is not following its own property. So if it is not following their own property, then what we will do is that we will fix heap. We will perform some operations, we will do some things. After that we will resolve the overall, you can say, overall structure of the heap, and we will finally fix the heap. So this is what insertion will happen. Now let us talk about how we're gonna fix it. So this is my array. After adding the new element, this is my resultant array, 2 3 4 5 10 and finally 1, and their indexes are 0 1 2 3 4 5. Okay, so this is my new array list, and it is not fixed. The heap is not fixed. Now I need to make some operations, and such that I need to fix my heap. So to fix my heap, there is a property. The property says that, let's say that newly added element, let's say that its index is x, then this property says that its parent index will be x minus 1 divided by 2. By using this property we will fix our heap. So how we are gonna use this property? Let's say that here, for example, the newly added element is 5, the newly added element is 1, and its index is 5. Okay, then its parent index will be, parent index is equals to 5 minus 1 divided by 2. It means that 4 by 2, that is nothing but 2. So its parent will lie here. This is the parent index, and this is the newly added index. Now what I will do is that to fix a heap, I will run a loop, and I will check the parent and child property, child values. In min heap I know the condition. If my child value is less than or equals to my parent value, if this is the condition I am getting, then I need to fix my heap. It is not a min heap, I need to fix it. So what I will do is that I will swap parent and child. I will swap the parent and child element. So what I'm basically doing is that here this 4 will come on one position and 1 will go on parent position. So my array will become something like this. After swapping, here you can see that 2 3 and 1 will come here, after 5 and 10 and finally 4, and the indexes will remain same, 1 2 3 4 5. Okay, now again I will check. My loop is not completed. I will continue my loop until my element comes on parent position, or this condition becomes false. If this condition is not true, then I will break my loop. Else I will go into the if statement, and this swapping process will continue until my whole heap got fixed. Okay, so for this is my child node, right? This is my child node, and I will check its parent. Here parent index is equals to, now one index is 2, so 2 minus 1 divided by 2, that is nothing but 1 by 2, and I am only taking the old values, so this will give me 2. So this is the parent index. Now you can see that the parent index value is greater than the newly added element. If this is the condition, then again swapping will take place. So my final array will become 1, 2, after that 1, 3, 2 and 5, 10 and 4, and these are the indexes 0, 1, 2, 3, 4, 5. So here this 1 will come on this and 2 will go like this. So this swapping will continue. I hope you have understood. Adding a new element in my heap is a two-step process. First of all, I will add that element on the last, and because of adding the element on the last, my heap is not fixed. So second step will be fixing my heap based on what heap I am having. If I am having a min heap, then I will check the conditions of min heap. If those conditions for this particular newly added nodes, I will check the parent value. If it is satisfying the condition of parent child, if it is having the condition of min heap, then I will leave it. If it is not having, then I will swap these two values. After that, I will check this swapped node, newly added node, with its again parent. So I will check if this both nodes are having if these both nodes are satisfying the conditions. Okay, no worries. If these both conditions are not satisfying, again swap these two values. This swapping will continue until my whole heap get fixed. So this is how the insertion will happen. I hope you have understood how we visualize a heap in the form of a binary tree and how we represent that in a array list. By using level order traversal, we will add, or you can say we will represent that in our arrays or array list, and this by using this two-step process we will add elements into my heap. I hope you have understood. Now let us code this thing. I will create a static class. Here I need to give class. Let's say that the class name is heap. Now I have told you that we gonna implement a heap using array list. So I will create an array list first. So array list of, let's say that I am creating integer type. So I will give integer and err is my name is equals to new array list. I have created my array list. Now after creating array list, let us add elements. So I am gonna create a function to add elements in my heap. So I will create public void add. In this I will pass data, int some data. What is the first step? The first step is add at last. So what I will do is that I will add the given data at the last index. So err dot add the data. I will add the data. So this add function will automatically add on the last. Now after adding last, I need to take the parent, the given index, the child index parent value. So int x is equals to, I need to take the newly added element, you can say index. So err dot size minus 1, because I have added last, so it index will become the last index, right? So the x will become the last element index. After that I need to calculate the parent index. So parent idx is equals to let's say that how we can calculate x minus 1 divided by 2. This is how we will calculate parent index. Now I am checking my I am running my loop to fix my heap. I have added the element in my heap. Now I need to fix the heap. So to fix heap, this is my step 2, fixing heap. So what I will do is that I will run a loop while err.get of x is less than err.get parent idx. If the parent value is greater than the child value, then inside what I will do is that I will swap the parent and child nodes. So how I'm gonna do? First of all, I will create a temp variable. Temp is equals to err.get x. After that, err.set. I will set at the child position, I will set parent value. After at parent position, I will set child value. So here I'm gonna at the x position, I'm gonna set err.get my parent index. Now after that, err.set At the parent position, I'm gonna set the temporary, whatever the child value I'm having, I will store at parent index. I'm gonna store. Now after that, I need to change the parent and child. Right now my child will become this newly parent. So here x is equals to my parent index, so my x will become my parent. After that, my parent will become x minus 1 divided by 2. Here I am adding my updation step. Here I need to give parent id x is equals to, okay. So this is how I will add elements in my given heap. Now before going to deletion, there is another operation called as peek operation, right? So let us talk about peek operation. Here I'm going to write peek operation. So in peek operation, what we have to do, we need to print the ARR of 0th element, whatever the elements present in my array list, whatever the element present on the top index, I need to print that element. That is nothing but peek operation. So what I will do is that I will create my function, and in the function I will return ARR.get 0th index. Whatever the element I am having at the 0th index, that will become my peek operation. That element will become my peek element. Okay, now let us code the peek operation thing. So here at the same time, I'm gonna create a function for public, and let's say I'm creating int type function, and the name of the function is peek. Now here what I will do is I will basically return ARR dot get 0th element, whatever the element present at the 0th index, I will return that. So this will give me big of constant time, because I'm not performing any operations. Whatever the element present in the 0th index, I'm returning. So this will give me constant time. Now if you observe this adding operation will give me big of log n time, because what I'm doing is I'm checking, right, in my whole array for some elements I'm checking, and after checking, if the condition is not satisfying, then I'm fixing my heap. So this fixation part will take big of log n time. That is why my whole adding process will become, the time complexity of adding process will become big of log n. Now let us talk about deletion operation. So talking about how we can delete a particular element, you can see that in the adding operation, it is a two-step process. In the first step, we added the new element at the last. After that, we have checked its parent value, and if the parent value is greater in min heap, if the parent value is greater, then we have swapped, and this swapping process will get continued until my whole heap get fixed. Right, got fixed. I have continued this process, this swapping process. Similarly, deleting a particular element in my heap is a three-step process. The first step is swap first and last element. Whatever the elements you are having, take the first element, take the root element, and the last element, whatever the element you are having at the last, take these two elements and swap both of them. After that, remove last element. After swapping, whatever the element you are having at the last, delete that. After that, the third step is fix your heap. Whatever the heap, unbalanced heap you are having, you need to fix it. And how we can fix it? By using a function called as Heapify function. Okay, so this is how we are gonna remove a particular element in my heap. So let's say this is my array, right? So this is my heap, and how we can visualize? We can visualize it as like this: 2, 3, 4, 5, 10, 6. So this is my array visualization representation. Okay, whatever. Now what I will do is that I will swap the first element with the last element. So my array will become 6, 3, 4, 5, 10, and 2. Now what I will do is that I will remove this element from my heap. So my array will become 6, 3, 4, 5, 10. Now if I draw the diagrammatic representation of this array, of this heap, then my heap will become something like this, will look like this. 6 will be here, after 3, after 4, after 5, after 10. This is what my heap will look like, and in this you can see that one got removed. I have removed one from my heap. Okay, now the question is this heap following the property of main heap? this is a min heap basically. Is this following the property of min heap? And the answer is no, it is not following the property of min heap. Now if it is not following, then what I will do is that I will fix the heap using a heapify function. Now let us talk about what is this heapify function. So in heapify function, what I will do is that I will pass the root node. Whatever the root node index I am having, I will pass the root node index, and this root node here, let me write the heapify function. So in the heapify function, what I will do is that I will pass the root node index. So I will pass int my root node index. Now what this heapify function will do is that it will check the corresponding left and right indexes, corresponding left and right child. If the given index, if the given right and left trees, or you can say childs, are having minimum values, then we will swap that minimum value with my root node. Okay, so what I mean by this is that, let's say that the left child, we already know that from the first property here, from the first property I have showed you that the left child, if the root node is I, then the left child will be this and the right child will be this. So what I will do is that here I will calculate the left child. So left child is equals to 2i plus 1 and the right child will be 2i plus 2. Now after taking this, I will compare which one is minimum. Whatever the elements present at ith element after 2i plus 1 index, after 2i plus 2 index, in this 3 indexes, which element is minimum, I will take that as minimum and I will store in a variable called as min, and after that I will swap the I, that is nothing but root element, with the minimum element. You can see that in this 3 root node, left child, right child, you can see that the minimum element is 3. So what I will do is that I will swap 5 and 3 values. So my overall heap will become 3, after that 5, after that 4. After swapping, if my tree is huge, if my heap is a big heap, then I will recursively call for the rest of the heap. I will recursively call heapify for the rest of my tree. So this is what I'm gonna do. In the heapify function, I will pass the root index as my parameter, and after that in the heapify function I will look at the left child and right child, and among these 3 root node, left child and right child elements, which one is minimum, I will take that minimum element and I will store it in a variable. Let's say that I am storing in a variable called as min. Now after that, what I will do is that this root node which is passed, this root node index which is passed, right? So I will swap the root node index with the minimum index. That's all. And after swapping, I will, if my heap is big, then I will call my heapify function for the rest of the array. And this heapify function will fix my whole heap automatically. Now let us code this thing. So here I'm gonna create a function public. Let's say that int type function, int remove. And in the remove, what is the main first step will be, step 1 is swap the first element and the last element. So what I will do is that I will store int data is equals to arr.get 0th index. I will store that. After that I will swap int temp is equals to arr.get 0th index. Now this is the swapping step. Here I am performing my step 1 swapping step. Now after that, here I will set arr.set. At the 0th index I will set my last index value. So arr.get arr.size -1. The last element, last index value, whatever I am having, I am storing it at the 0th position. Now after that, arr.set at the last position, arr.size -1 at the last position, I am gonna store the temporary value, which is nothing but my first data. Now my step 1 is completed. After that, my step 2 is delete last node or last element. So what I am gonna do is I will write arr.remove, and here I will give arr.size arr dot size minus 1. At the last index, whatever the element I'm having, I'm gonna delete it. Now after that I need to call my Heapify function. This is my step 3. Step 3 is call Heapify function. Heapify, and here I'm gonna pass my root index. The root index is 0, so I will pass my root index. After that, finally what I will do is, this is the int type, the return type of this function is int, so I will return my data, whatever the data which I have deleted this, right? So I'm gonna return that data. That's all. Now let me define the Heapify function. So I will write public void. Let me give it as a private function, because I don't want anyone to call my function, my Heapify function outside of my class, because if they are calling, then what's the use, right? Let's say that if I need to call my Heapify function only if my heap is not fixed. If it is fixed, then what's the use of calling Heapify function? That is why I'm making it private. Now here I will give private void Heapify. In this I will get the root node index. Now here I need to store the left child index. So left child is equals to 2 into I plus 1. According to the formula, according to the property, this is the formula. And right child index will be 2 into I plus 2. Here let me give the parenthesis such that I can understand multiplication will happen first. Okay, now after that, what I will do is that I need to check which one is minimum. So let us consider that my minimum index is I. Now after that, what I will do is that I will check my conditions. If my left is not greater than arr dot size and arr dot get the minimum, at the minimum index, whatever the arr dot get value I am having, that index, if it is greater than arr dot get the last element, that is nothing but my left child. If this is the condition, then I need to change my minimum. Here I need to give LC, not left. Okay, so here if I got this condition, then I need to change the minimum index. So my minimum index will become left, LC. Now similarly, same condition will go here, that if my left is greater than arr dot size and arr dot get the minimum index is greater than arr dot get my right child. If this is the case, then I need to change my minimum index as right child. If this is the case, then I need to change like this. Now after that, if my minimum is not equals to, if my minimum index is not equals to my ith index, it means that the heap is not fixed. Then what I will do, I need to fix the heap. So what I will do is that I will swap the ith element and the minimum index. Ith index and the minimum index, I need to change it. I need to swap it. So what I'm gonna do is I will write int temp is equals to arr dot get ith index. After that, arr dot set at the ith index. I need to store arr dot get whatever the element present at the minimum index. I need to store in the ith index. Now after that, I need to store arr dot set at the minimum index, and I'm gonna store the temporary value. That's all. This is how the swapping will work. Right, this is the overall working of Heapify. Now in the main function, what I'm gonna do is I will create a heap. Here I need to create heap. Let's say I'm creating a heap and the name of the heap is h is equals to new heap. Now after that, I'm gonna add my elements in the heap. So I will add h dot add, and let's say I'm adding 0. After that, h dot add 10. After that, h dot add 2. Now after this, I'm gonna print the elements, whatever the elements I have added in the heap, I'm gonna print that element. So while my heap is not empty, let me define the function of empty also. Public boolean is empty let me define the isEmpty function also. If my, how we can say that whether the heap is empty or not, if the array, whole array is empty, then the heap is empty. So I'm gonna return here, return arr dot size. If it is equals to 0, then I will return true, else I will return false. So if it is not empty, if h dot is not empty, if this is the case, then what I will do is that first of all I will peek here, I will peek h dot peek and give a space here. After it I will remove h dot remove, I will remove the element, whatever the elements I have added, I will remove them. Now let me save and run. So you can see that I got the output as 0, 2, 1, and this is what I wanna say this to you guys. So priority queue, we have studied priority queue, right? So how priority queue works is, internally it is a heap. So the overall internal operations that goes in the priority queue is basically heap operations, and this is how we will perform operation, this is how we will check, this is how we will add operation, we will peek, we will like remove operation by this. I hope you have understood the overall approach of the like how we can add, peek, perform operations like add, peek and remove operations in my heap, and what is a heap, how we visualize it. And one more thing you need to remember is that we visualize it using binary trees, but we implement heaps using arrays or array lists, and priority queue works internally based on the concept of heap. So with that being said, we have seen what is a priority queue, operations involved in it, what is a heap, how we visualize it, how we implement it, and by this performing these operations we can implement a heap in our program. And in the next session again we will continue with heap, and in the next session we will talk about what is heap sort and some important problems based on heap. So with that being said, I will see you in the next one.